Hey everyone, welcome back. We're learning more math, sorry to say. So let's get to it. So last time we finished off talking about discrete random variables, and we learned about one special case, which was the binomial probability distribution. And we learned everything that we can mainly do with that binomial probability distribution. We learned about the binomial probability distribution function and how to calculate various probabilities using that function. So that was all for the discrete case. Now we're moving into the continuous case. So we're going to be looking at continuous random variables. And there's a whole lot of continuous random variables, or I should say continuous probability distributions, different ones that we could study. But we're going to be focusing only on a few of those in this class. And as you'll see, these are actually super important and useful. So let's jump right in. So as I said, we're talking about continuous random variables. So now we're not just dealing with discrete sets, but continuous sets. And so everything that we talked about in the context of discrete versus continuous previous in the class applies here, okay? So the first definition we need to cover is what's called a probability density function, okay? So we had a probability distribution function for the discrete case, but now we'll have a probability density function in the continuous case. So it works just like the PDF that we learned about for the binomial distribution, except now everything's continuous. So just like the probability distribution function for the binomial, the probability density function for a continuous random variable has two properties, which should seem pretty familiar to you. So one of the properties is that the total area under the graph of this PDF should equal 1. So this is just like what we talked about for probability distributions, where one of the properties of a probability distribution was that the sum of all probabilities must equal 1. So this is exactly the same property, just in a different, in a disguise, okay? So all PDFs must have this property for continuous random variables. The second property is that the height of the graph of this function should always be greater than 0, right? And theoretically less than 1. So this is just like the other property that we saw for distributions, where if we looked at each individual probability for a distribution, each probability should be bounded between 0 and 1, okay? So probability density functions really are just a mathematical formula that can be used to probe a particular distribution. So it really, this function captures everything that would have been found in the table for a probability distribution. But now, instead of having to list all the possibilities, we just have a nice, pithy, succinct function that we can use instead of having to use a table. Okay, so let's look at an example of a continuous probability distribution and also a probability density function and how we can use it to calculate probabilities. Okay, so the first stop is for the uniform probability distribution. So we learned about uniform distributions when we were first learning about the shapes of histograms. And so here we're finally going to be working with it. So a uniform distribution, as we discussed previously, is a symmetric distribution. So it's got symmetry about its mean. And really, it's the most primitive and basic distribution that you can imagine. Okay, so it's all of the possibilities for a uniform distribution are all equally likely. So any particular event, simple event, I should say, any simple event has the same probability as any other simple event. Okay, so let's look at this example. I'm going to define a random variable. This will be a continuous random variable x that measures the time of arrival between noon and 12:30. Okay, so it measures it in the number of the minutes that have passed since noon. Okay. Now I say that all times between noon and 12:30 are equally likely, which tips me off that this is uniformly distributed, this random variable. So if I plot a graph of the density function for this random variable x, it would look like a rectangle. This is what all uniform distributions look like. There's some sort of rectangle. The rectangle has a base between 0 and 30, which represents the number of minutes that have elapsed from noon to 12:30. And on the vertical axis, we see that we have the probability, and the probability is all events are equally likely. So there's a fixed probability of 1/30. So arrival for any given moment between 0 and 30 minutes after noon has an equal probability of 1/30. Okay, so let's see if this is indeed this does constitute a graph of a probability density function. So looking at it, first off, we can see that all of the graph is above the x-axis, above the horizontal axis. So that tells me that all the probabilities are positive. They're also all less than 1, since it has a fixed probability of 1/30. So everything's below 1 and above 0. So that's a check. The second property is that if we look at the total area underneath the curve, that total area should equal 1. Well, in the case of a rectangle, area is easy to calculate. Area is length times width. So for this rectangle, we have a length of 0 to 30. So that's a length of 30 and a width of 1/30. So that indeed does equal 1. So if we calculate the area of the total rectangle, we get 1, which tells us that between all of the probabilities being positive and less than 1, and the total area being equal to 1, we have a valid probability density function for this uniformly distributed random variable x. Okay, so this idea of calculating the area under the curve is a really useful idea. And moving forward, while we're working with continuous random variables, we're going to use this area idea to calculate various probabilities. So let's take a look. All right. So we're working with the same example, but now we're going to calculate a few different probabilities. Okay. So the first thing we want to do is calculate the probability that we will arrive between 5 to 15 minutes late. Okay. Now, as I said, probability is equal to area. So if I draw my uniform distribution, which is the rectangle that goes up to 30 and it has a height of 1/30, I'm looking to calculate this probability. I'm looking for the area between 5 and 15. So I'm looking for the area of that little shaded rectangle. Okay. Now, I should really provide you with a probability density function to work with. And for a uniform random variable, the probability density function really is just 1/30. It's equal for every given x has the same probability. So it doesn't really do us a whole lot to know what the density function is explicitly here, because we can't directly use it to get an area. At least it doesn't seem like we can. But I can give you another useful formula. It says if I want to know the probability of our random variable being between two values, so here's our big X, and I'm saying, what's the probability that big X falls between X0 and X1 for a uniform distribution? This will be equal to the fixed probability for that distribution, little p, times X1 minus X0. Okay, so if we use that for our problem here, we're looking for the probability that big X is between 5 and 15. Our fixed probability is 1/30. So we put 15 and 5 in for X1 and X0 and calculate. So that's going to be 1/30 times 15 minus 5, which is 10. So that equals 1/3. So the probability of arriving between 5 and 15 minutes late is 1/3. And this makes sense. This 1/3 is also, if we think of it geometrically, is the proportion of this shaded in rectangle to the bigger rectangle. So the big rectangle is 30. This rectangle has a width, a length of 10, which is 1/3 of 30. So that makes sense geometrically. Okay. So we could also ask a different question that still relates to this idea of using area to calculate probability. So the question would read something like this. There is a 20% chance of arriving before what time? Okay. So we want to figure out what, if we start the clock at 0, how long will we wait, knowing that there will be a 20% chance that the person that we're waiting for will arrive by a certain time. So sorry about that. I keep having issues with Zoom. It's a pain in the butt. So anyways, let's calculate this second type of probability. So here I'm being asked to find what is the latest that someone can arrive according to this particular probability distribution, so that such that they will arrive, that there's a 20% chance that they will arrive by that time. Okay, so this seems a little tricky, but we can do this. So what we're going to do is say this. We're looking for the probability that if we start the clock at 0, we want to know by what time X will we arrive such that the probability will be 20%. So using this function that I showed you up here, what we're looking for is to solve for X such that it solves this equation. So this simplifies to 1/30x equals, and I'm going to go ahead and convert this into a fraction. So that's 1/5. That's 20%. So if we solve for X, it's going to be 30 divided by 5, which is 6. So if you, what this answer means is that as long as you arrive before, there's a 20% chance that an individual will arrive by 6 minutes after noon. So this is still using area essentially to solve for probability for a uniform distribution. Okay. So uniform distributions are great. The area calculations are very simple, but uniform distributions do not, in general, model very much of reality, because it's very seldom that all likelihoods are equally, or that all possibilities are equally likely. A far more useful distribution is what we call the normal distribution. And we've learned about this before, again, when we were talking about the shapes of histograms. So we say a continuous random variable whose histogram looks like a bell curve is called normally distributed or has a normal probability distribution, right? And so remember, this is the bell curve right here. So if we look at the distribution function for a particular random variable and it looks like this bell curve, then we would say, hey, it must be normally distributed. Okay, so this is a continuous random variable, by the way. And if we know that the random variable is normally distributed, then we know that it satisfies a certain number of properties. Okay, so this is in the context of this curve. We'd say the properties of the normal curve are, first, that it's symmetric about its mean mu, right? So the mu is its mean and it cuts it in half. So it's symmetric about mu. The second property is that its mean, median, and mode are all equal to one another. So it's a unimodal distribution. It has one peak, and the median and the mean are always equal for a symmetric distribution, as we've learned before, right? So we know that we have a single peak at x equals mu, right? This is the x-axis. Okay. The next property is that we have something called inflection points at at x equals mu plus the standard deviation sigma and x equals mu minus the standard deviation sigma. So here's mu, here's x plus sigma, here's x minus sigma. If we look at the graph at those particular points, we say that these are inflection points. Inflection points are sort of complicated to describe fully in a mathematical sense, but the idea of inflection point is, I guess, rather simple geometrically, which is that what happens at an inflection point is what we say the concavity of the graph changes. So basically here, the graph is concave, and then right after this point, the graph becomes convex. So it flexes up. So here it's opening downward, and then here it's opening upward. So that's what an inflection point is. It marks the place where we go from opening downward to opening upward. And those inflection points for a normal curve must occur at the mean plus the standard deviation and the mean minus the standard deviation. Okay. The fourth property is that, as with all distribution functions and their curves, the total area under the curve must equal 1. So this just goes without saying. The fifth property is that the area to the right of mu must be equal to the area to the left of mu, which of course follows from the fact that we have something that's symmetric. So if we look at the area to the right of mu, that's this area here shaded in, that must be equal to the area to the left of mu. And since mu is equal to the median for a symmetric distribution, we know that those two areas must equal 1/2. Okay. And then the final property is that if we look at the curve as the variable x approaches infinity to the right and negative, as the variable x approaches infinity to the right and negative infinity to the left, the curve gets closer and closer to 0, or closer and closer to the horizontal axis. Now, it looks like they touch in the way I've drawn it, but in reality, the graph never actually reaches the horizontal axis. It gets closer and closer and closer, but it continues on forever to the right and forever to the left, never actually touching. So the way we say that very succinctly is that as x approaches positive infinity or negative infinity, the probability approaches 0. It never quite gets there. It doesn't equal 0. It approaches 0. Okay. So as a distribution, the normal distribution has a PDF, or a probability density function. And I'm going to write it down for you so that you can see it. But I'm sure that a lot of you, as soon as you see this, will think, holy crap, that looks insane. I really hope I don't have to do anything with that. And aside from maybe having to plug in a value for x into this function and evaluate, you won't have to work with this at all, okay? So this is just here to show you what the probability density function looks like for a normal distribution. It's this very complicated expression that somehow involves a pi, somehow involves an exponential e, and yeah, it's complicated. So this is the density function, which we would use to calculate an individual probability. And if we wanted to calculate a range, the probability of a value falling within a certain range, which is to say the probability that our big X will fall between some x0 and x1, then theoretically, the way that we calculate that probability is using this complicated integral. Okay, an integral is something that you would learn in calculus, and we're not going to use integrals at all in this class. Do not worry. You're not supposed to know any calculus to do this class. But I wanted to show you that this is how we do it mathematically using this integral, which is really sort of the continuous version of the sum. So you know what that means for discrete. So for continuous, the S here is sort of the analog to the sigma. So for continuous, you use an integral. For discrete, you use a sigma. Don't worry about it. We will not be doing this physically in this class. We'll only use calculators to calculate this. But if you wanted to, you could do it by hand and define the probability that our big X falls between x0 and x1. We'd use this integral, which would tell us what the area is between x0 and x1 on this normal curve. Okay. So this area represents a probability that the random variable will have an output that falls between x0 and x1, okay? And that should be given by the actual physical area underneath the curve there. So next time we will learn about how to actually calculate what this area is, and therefore how to calculate individual or particular probabilities, okay? In this section, we're just introducing it. In the next section, we will learn how to actually calculate probabilities, okay? So that concludes section 7.1. We've learned about continuous random variables, the uniform probability distribution, and the normal probability distribution. Heads up, there will be a quiz this week. It will be online. I will make an announcement specifying all of the parameters. I'm likely going to make it due. I'm going to give you over the weekend to complete it, and maybe up to 3 attempts to complete. But it will be your responsibility to complete the quiz, which will cover, I think, just conditional probability, if memory serves. But I will have all the specifics in an announcement. Okay.